Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. So here you can finally see some picture. Okay, so this is the picture of a star which is oscillating. So let's say this is the initial condition, initial state at rest, and then after perturbation, this pink lines. Okay, this is the perturbed figure. Okay, and you can actually see that more or less if you are at a distance like r from this one, from this center, so more or less you are having the same nature of the perturbation. Okay, whether you are, I mean, irrespective of whether you are here or you are here or you are here. So this is a rough image. Of course, we know that pure radial oscillation or pure radial perturbation is an idealization in this case. So in general, we can just think that this type of figures are there. So roughly considering, this is radially symmetric. And then we actually think that we just consider the equations of motion, or the Newton's equation for a fluid element, so which should be considered as a particle here, and we will write the force equation for that. So that this particle is situated, let's say, at a distance r from the center. Okay, so if the particle's velocity is v, then dv dt, so dv dt is nothing but, if you remember, in terms of the Eulerian derivatives, that is equivalent to del t plus v dot nabla v. Okay, so this dv dt is equal to minus 1 by rho dp dr. Why this is dp dr? This is in general gradient of p, but here once again we are only considering the system in the radially symmetric direction. So the only component, only ddr will survive. Del theta, del phi will not survive. So del r basically now has become ddr. Okay, so this is something is given. Okay, so and minus gm by r square. So this is the pressure gradient force, and this is the gravitational force due to, so this is the gravitational force due to self gravity. So this so that's what I have written over here, that this equation is for a fluid element which is situated at a distance r from the center, and the m is the mass of all the star which is inside, which is situated from 0 to r, the whole mass. Okay, the whole mass, for example. Okay, so basically because the fluid element, it how to say, it experiences the gravity field created by the whole mass which is inside the radius r, right? That's the meaning of m. So what happens at the initial state? So our initial state is assumed to be not only a steady state but a static state. So we just say v is 0 and dv dt is also 0. So the pressure gradient force will simply be exactly balanced by the self-gravity if you just refer to this equation. Okay. Now let's assume that due to a spherically symmetric perturbation, the star is expanded uniformly in all directions. Okay, and the fluid element which was initially at r0 will now be situated at some r. So we now say that, okay, that was the generic variables r, v, so, and it was also not, so this equation is true for initial state, for current state, any later state. Okay, so we are now calling all the initial variables at as R0, rho 0 and rho 0, and for example if you will see that P0. So rho 0 is the initial density, R0 is the initial so rho 0 is the initial density of the star, of course, and the R0 is the initial distance coordinates. Of course, you can also think of the position of the fluid particle. Okay, so rho 0 is, of course, you can think that this is the density of the fluid particle at that which is situated at R. Okay, which is situated at R0. So this is the initial density. Okay, and finally, just a minute. Yeah, and P0 will be the corresponding pressure, initial pressure. Okay, so now what we will do, we will simply perturb the position of the particle from R0 to some value R, where R is nothing but R0 times 1 plus delta, and this delta is greater than 0, but what I forgot to write is delta is very, very less than 1. It's a very small perturbation. Okay, and if this is true, then the density of the star can be written as rho is equal to rho 0 times 1 plus delta to the power minus 3. That is simply because the volume increases from V0 to V0 times 1 plus delta whole cube. If the radius increases like this, then the radius cube will be increasing like this, and so the volume will be proportional. Volume increase will be proportional to this factor, and if delta is very, very small, it will be simply 1 plus 3 delta, approximately this factor. And so for the density, it is actually reducing, because density is nothing, mass by volume, and the mass is unchanged for the system. Okay, so maybe I was maybe at some point I said something a bit confusing, that this rho 0 is the initial density of the whole fluid. Okay, this is not the density of the fluid particle, of course, but this is the density at the point R0, at the point R0. That's for sure true. Yeah. Now this density is now changed to this density. Of course, this is not a representative density, this is just the variable. Okay, so initial variable was this, final variable after perturbation is this, but they are actually changing from one point to the other. Okay, so that is something to not to forget. Okay, and the volume is increased because we have dilated the star a bit by dilating the radius, so the density will reduce by this factor, and then it will be becoming almost rho 0 times 1 minus 3 delta. Okay, now we have assumed polytropic closure. So P will be, if rho is decreased by this factor, P will be decreased by this factor to the power gamma, and that's exactly what I have written over here, times the initial pressure. So the final pressure is equal to the perturbed pressure variable is equal to the initial pressure variables times 1 minus 3 gamma delta, and that's true for every point of the fluid, right? This is just relating the initial variables, initial set of variables, and the later state of later set of variables, like current set of variables. Okay, if this is clear, then you can easily say that for initial state, I can just write the balance equation of the pressure gradient force and the self-gravity force using the initial coordinates. That's exactly true. 1 minus rho 0 times dp0 dr0 is equal to gm by r0 square. And for current state, I write the equations with the current variables. dv dt is equal to minus, so dv dt is no longer equal to 0, so this will be equal to minus 1 by rho times dp dr minus gm by r square. But rho is nothing but rho 0 times 1 minus 3 delta. P is nothing but P0 times 1 minus 3 gamma delta. Rho is again nothing but R is nothing but R0 times 1 plus delta. And here R0 square will be nothing but r square will be nothing but r0 square 1 plus delta square, and which is almost equal to 1 plus 2 delta once again, just keeping the terms up to first order. Now if we do that, finally we can say that this is nothing but 1 minus 1 by rho 0 dp0 dr0 times the whole factor 1 minus 3 gamma delta by 1 minus 3 delta times 1 plus delta. Now 1 minus 3 delta 1 plus delta gives you 1 minus 2 delta minus 3 delta square. Again 3 delta square will be neglected, and we will have simply 1 minus 2 delta at the denominator. 1 plus 2 delta in the denominator will become 1 minus 2 delta in the numerator, right? Delta is of first order once again. And then finally you can write this 1 minus 2 delta whole to the minus 1 will become 1 plus 2 delta. So 1 minus 3 gamma delta times 1 plus 2 delta finally gives you to the first order 1 plus 2 delta minus 3 gamma delta, and this will be multiplied with the initial pressure gradient force term. Okay, minus the initial self-gravity force term times 1 minus 2 delta. So this is the factor which is now multiplied with the initial term, and we know this one is equal to this one due to this relation. We know this one is equal to this one. So finally we take the just replace this one by this minus minus 1 by rho dp0 dr0, and finally we can get this whole thing dv dt will be now equal to minus 1 by rho 0 dp0 dr0, and within bracket 1 plus 2 delta minus 3 gamma delta minus 1 plus 2 delta. Okay, and what is this? This is nothing but 4 delta minus 3 lambda delta, sorry 3 gamma delta, sorry extremely sorry 3 gamma delta. Okay, so finally what we obtain? So finally we obtain that dv dt is equal to minus gm by r0 square times 3 delta within bracket gamma minus 4 by 3. So this is the final equation actually. Okay, this is the final equation one should write for the acceleration of a fluid particle situated at a distance r from the center. Okay, now the acceleration can be negative, can be positive. Now what is the implications of that? We were trying to dilate the thing by putting some outward perturbation to the radius. So we tried to increase the radius, right? Now if the acceleration, so of course you know, like these two forces, I mean the gravity and the pressure gradient force, the acceleration is also radially directed. And if the acceleration is radially directed, then this will be positive. If this is positive, that will simply indicate that the system will be dilating, and if this is negative, then this will indicate that the system will try to get back to its original position, so it will counteract the act of dilatation. And when dv dt is greater than 0, simply because g, m, r0 squared, 3 delta all are positive, so the only possibility that this becomes greater than 0 only when gamma is less than 4 by 3. Then only this part is negative, and this part is negative makes the whole thing positive. So if gamma is less than 4 by 3, then the system, if dilated a bit, it will continue expanding, thereby supporting or enhancing the dilatation, and that's why we will have instability. However, if you have gamma greater than 4 by 3, then the acceleration is actually in radial direction, but in inward direction, because then it will be negative. This thing will be negative, the total thing, because this is positive. Then we will have the acceleration is in the radially inward direction, and so opposes the expansion. and then it leads to the stability. Now here at this point, just think a bit. We understand the result is interesting, the result is simply obtained, so we have enough reason to be happy. But before being happy, just think what is the physical reason, because finally we are doing some astrophysics. So some physical reasons should be thought. Why why it is like that when gamma exceeds critical value, let's say 4/3, okay, finally gives a rise to the stability, otherwise it is unstable. Of course, a very simple and very apparent explanation is there. That is, whenever you are trying to perturb the system, let's say by increasing the density, for example, then what happens? Then you are just increasing the density at one point, and so the self-gravity force will be important at that point. But if your density is increasing, due to your polytropic closure, your pressure will be increasing, and that will actually increase the hydrostatic pressure to balance the effect of the self-gravity. Now, if your gamma is higher and higher, higher than some critical value, okay, then some increase in density will make the increase in pressure so important that it will be enough, or it will be sufficient to counteract or counterbalance the gravitational effect, self-gravitational effect, or collapse type of thing efficiently. Whereas if gamma is less than this 4/3 value, then what happens? Then the pressure perturbation is not sufficient to counterbalance the gravitational effect. And the same thing can be actually thought if we decrease the density. Okay, so for example, here we are just decreasing the density. So we are decreasing the density, the self-gravity force basically decreased, but with the decrease in density, how the decrease in pressure will act? Because if pressure wins again, so here we are trying to curb the gravitational force. So if the pressure is still very much enhanced, then it will actually expand. So we can have actually two types of instability. One is instability by expansion, one is instability by collapse. Both should be counterbalanced by their corresponding enemies. Okay, so here you will see that we try to dilate the system, and then this dilatation is actually counterbalanced by the reduction in the hydrostatic pressure gradient force. Okay, so and this is exactly the same mechanism by which one can actually think of stability and instability in this framework. Okay, now when stability is there, then every time you are increasing or decreasing the density, so you make a change. So increasing and decreasing density means increasing or decreasing the gravitational effect. Okay, so your pressure should be efficiently increased or decreased respectively, so that you can nullify or counterbalance as soon as possible the effect caused by the perturbation. So that is the very apparent and straightforward discussion. Now it is true that there is an interesting thing about 4/3. So 4/3 actually, maybe not really directly related. So it has a very interesting importance in this number 4/3 in the context of Chandrasekhar limit. Okay, so you search and you let me know that whether you got it or not. Okay, this is very interesting for 4/3. So like for a normal gas, for normal classical gas, what is the adiabatic index? If it is consisting of monatomic gases, it's 5/3. Can we have some gas for which the adiabatic index is 4/3? Check. Okay. So these are very interesting things. And also I said that there is a relation with that and Chandrasekhar limit. Okay. Anyways, coming back to our question, that here we have not done proper linearization, proper dispersion relation. We have just taken a fluid element and we have tried to analyze its motion, whether it is after under dilatation, whether it is trying to accelerate outward or inward. Very simple. Of course, this type of simple analysis is good for symmetric cases, and actually if you do the formal calculations, you can actually see that the stability criteria which we get here is exactly the same. That is, gamma should be greater than 4/3. Okay. Now one can actually do a proper analysis, and from that one can also think of can find out the stability criteria. Okay. Now what happens, so here in this case we have done very simplified radial oscillations, but what happens if we consider non-radial oscillations? Can we have something better? Something much more formal? Then should we do something much more formal? Well, then actually this system, the solution is no longer as simple as this. As simple as this. Then here you will have also something called YELM. There will be another two other index which will be the function of theta and phi, and they are known as spherical harmonics. If in case you don't know, search for it what they are. So in case of non-radial oscillations, we have to use the spherical harmonics. Okay, and we have to perform a formal analysis process. Okay. Finally, the question is that if the radial oscillation is so simple, why should we at least at all think about non-radial oscillations? Because let us now have a look at the reality. And what is the reality? Our neighbor and our the central star of our solar system, this is Sun. How can we forget that one? And actually, like Cepheid variables, Sun is also an oscillating star. But Sun is full of non-radial oscillations, and solar oscillation is a subject of very, very interesting and ongoing research. Okay, so many people are working currently on this subject of solar oscillations, and this is known as the subject of helioseismology. Okay. In general, when we are talking about the subject of the oscillation of stars, we talk about the asteroseismology, and just for the Sun, this is known as helioseismology. Okay, so since Sun is full of non-radial oscillations, a careful and thorough analysis of the perturbation and deriving the dispersion relations is the only way. We cannot evade that, cannot avoid that. And here in this picture, you can actually see that this is one of the schematic picture, and this picture is actually taken from internet, so courtesy to NASA. Okay, so this picture gives you a clear idea about the oscillation at the Sun's surface. Okay, so this is the oscillation at the Sun's surface. So the oscillation at the Sun's surface was actually first established by three people: Layton, Layton, Noyes, and Simon in the year 1962. So this is much more recent. And finally, whether they are just, then the people actually thought that maybe some oscillations were there at the surface, and then people thought that maybe they are local oscillations and they are not global. But for, I mean, how to understand whether this is just a local oscillation or local perturbation, or this is not really something related to the global, I mean, global mechanics or global dynamics of the star, we have to actually then find the corresponding eigenfrequencies. If the eigenfrequencies of those oscillations match with the eigenfrequency of the global system, okay, global star, okay, including its geometry and the boundary conditions, then this is an indication, this is the indication that the oscillations which we see at the surface level, they're actually the oscillation of the whole body, okay, due to the whole body. So we discussed much earlier two type of forces, body forces and surface forces. So it's all, so I always love to make analogies in this philosophical part. So here this is also like body oscillation and surface oscillation. So surface oscillations, if this is totally uncoupled from body, then this is not of interest. This doesn't belong to this current analysis. But if this is a part of the bulk oscillation, then this is something which we are now studying. We are now studying the body oscillation thing. Okay. So for the first time, if you see that Döbner in the year 1975, he actually showed that this is actually related to the proper oscillation of the sun, and this is the related to the eigenfrequencies of the sun's bulk, okay, the sun's body, okay. And then the proper development of his helioseismology was caused, or was brought into the picture. And now it is of course a question that why this is useful, because helioseismology, other than the oscillation mechanism and the luminosity and the variable, the luminosity and the temperature variations of the star, of the sun periodically, there is another very interesting and fundamental useful, utility of the helioseismology, that is that this helps us know about the differential rotation of the sun. And actually the sun is rotating, we all know, and this sun does not rotate like a solid body. So every single, the concentric spherical shells or layers, they are rotating with different angular velocity. And by using proper analysis of helioseismology, one can actually know what is the variation of this, and what is the dependence of the angular velocities of radial dependence, or in any case, the dependence of the angular velocities in various parts inside the body of the sun. Okay. So that was all for this. Of course, if you are further interested, you can check all the books and the internet. There are very good books about this. So one book which is very intensively discussing the sun's oscillation, or rather star's oscillation, but mostly non-radial part. That is the book by Uno Osaki. Okay, so you can see the book's name is non-radial oscillations in stars, maybe. Okay, I am just not sure, but this type of name. Okay, so just have a look. You have also on internet so many things. So this is a very, very interesting topic where you can actually find your topic of research as well. Okay, so that was all about the waves, oscillations, and instability, linear instability part for our course. So in the next discussion, we will start a new topic, that is the effect of rotation in astrophysical fluid dynamics. Okay, thank you very much.